low pass filter design. Okay. Now, to design, first of all, see the main motivation of analog filter design is what is the main motivation? If you go for digital filter design, you require two analog filter. One at the starting, yes or not? One starting low pass filter, and at the end again you require another low pass filter. Getting? And and in digital filter also, what to do? You have to convert analog to digital, then again you have to convert digital to analog. Yes, sir. So here directly we can go for analog low pass filter design. So there is no A by D or D by A circuit required. Okay, and this analog filter means, you all people know this analog filter means what? It process analog signal. Yes or not? Simple. Your analog filter, like your analog system only, analog filter, it processes analog signal. Yes or no? Your input is analog signal and output also analog signal. If you see digital filter means this is it is a, if you see digital filter, it process digital signal. Okay, it process digital signal means input is digital signal and output also digital signal. Okay. Now this is the simple differences between analog filter and digital filter. Filter part you people understand. The simple analog filter is a system. It is you process the analog signal, and digital filter also is a system. It process the only the digital signal. Okay. Now the important part in both cases is the specification. That is very important. What are the specifications you are using? Okay. So important part is here. I'll write the specification. Okay. Now the specification is very important. Whenever you will design, you have to go for the specification. You cannot go beyond the specification. That's why if you purchase any electronic device, you can find the specification of that device particularly. Okay. Now see ideal low pass filter. So this is the ideal low pass filter. We can say, see, this is your ideal low pass filter. Last class I explained only. Okay, this is the ideal low pass filter. The magnitude is 1. Clear? Now this is your, you can put line like this. This is omega p. This is omega s. Okay, 0 and this is your omega p, or you can take 1 minus sorry, this is del p. You can take 1 minus del p also. Okay, both are correct. This is del of s. Okay, then these are the specifications. Your omega p, sorry, del p, del s, omega p, and omega s. These are the specifications. What is del p? Del p is attenuation in passband. Attenuation, or you can say ripple also, or noise also you can say. Attenuation in passband. Okay. What is del s? Del s is your attenuation in stop band. Okay. This is clear. This is your passband. See, this is your passband. Already I explained in the last class, and this is your stop band. Yes or not? Okay. And what is this omega p? This omega p. See, this capital omega I am using. Okay, for analog we are using capital omega, and for digital part we will use small omega. This capital omega p. This is what? Angular frequency in passband, or frequency in passband, or frequency in radian per second in passband. Okay, so this is, we can write passband frequency. Okay, in radian per second. That is important. You should not confuse. It is in radian per second. Okay, that is we can write like this 2 pi fp. Yes or not? This FP is the passband frequency in hertz. Similarly, omega s, this is your stop band frequency in radian per second, and this is your 2 pi fs. This is the stop band frequency in hertz. Okay, clear? So this is very, very important. These are the specifications for analog low pass filter. Okay, it's del p, del s, omega p, omega s. Now what we will do, we will use these specifications, okay, to design the filter or to find the transfer function of the filter. That is very, very important. Okay, this is your h of j omega magnitude. Okay, so this is your low pass filter. Clear? Yes or not, all of you? So this is simple ideal low pass filter. We'll design the ideal low pass filter. Okay, so here the passband range is 0 to omega p. It's very clear. Or you can say that it's 0 less than omega p is your passband, and omega greater than omega s, this is your stop band. Okay, and in between omega p to omega c, again it's very simple. Last class already I explained. So this is your passband. Okay, this part is the passband. Passband means 0 less than omega p. Okay, and this portion is your stop band, omega greater than omega s. This is your stop band, and this portion, see this portion, this is your transition band. Okay, transition band means omega p less than omega s. This is your transition band. Clear, all of you? Yes or not? Hello?
Yes, sir.
CND.
Yes, sir.
Okay. So this is already explained last class. So this is 3 because say in case of ideal, you will not find this transition band, but since we will go for practical design, that's why I'm showing all these 3 parts. This is the ideal low pass filter having sharp cutoff frequency. Okay, sharp cutoff frequency, but we will go for the practical filter. In the practical filter, 3 reasons are there. In case of ideal, only 2. In case of ideal, only you will get passband and stop band. But in case of practical, 3 reasons you will get passband, stop band, and transition band. Okay, and these are the very, very important because these are the specifications. Okay, we have to take this specification. It's very, very important. Okay, clear? Now we'll go for design.
So that is 0 greater than
Yes, which one?
passband, near passband.
Passband 0 less than omega p means omega lies between 0 to p.
Yes, sir.
This omega, this is your omega. It lies between 0 to p. That is your passband. Okay. Clear. Now, see. We will use these specifications. Okay. But before that, that is very clear, you all people. Okay. If you want to show again, I will show you here in big diagram. Omega p, omega s, 0, 1. This is h of j omega del P, okay, del S. Clear? So here all the three bands will get simple 0 less than omega P. This is your pass band. Then omega P less than omega S. This is your transition band. Because why it's the name is transition band? Because it's transiting from omega means pass band to stop band. Yes or not? Means the transition period. Okay, it's a transition period. And when omega greater than omega S, this is your stop band. Okay, so this is your ideal low pass filter. Okay, and this rest part you all people know. This omega P is a pass band frequency in radian per second or angular pass band frequency. This is your angular stop band frequency, attenuation in pass band and attenuation in stop band. And some book it is given like this: 1 minus del P. That is also correct, no problem. Okay, some book it is given 1 minus del P. So don't confuse. This is also correct. Okay, I will when I will explain, I will go for both del P and 1 minus del P. You should not confuse. Okay, this is the clear. Now we'll come to Butterworth filter. Now Butterworth filter. This is very, very important. Okay, the transfer function of the Butterworth filter is given by h of j omega square equals to 1 by 1 plus omega by omega c to power 2n. Okay, so this is the transfer function of the Butterworth filter. Clear? Again, I am repeating, this is a transfer function of the Butterworth filter. H of j omega square equals to 1 by 1 plus omega by omega c to power 2n. Okay, or we can write like this: H of a j omega magnitude equals to 1 by square root of 1 plus omega by omega c to power 2n. Here n is order of the filter. Okay, here n is the order of the filter. Okay, means first order, second order, third order, fourth order, like this. So this n is the order of the filter. Clear? And see, this is your Butterworth filter transfer function magnitude h of j omega magnitude equals to 1 by this much square root of 1 plus omega by omega c to power 2n. Now at omega equals to at omega, always I will use capital omega because analog filter design. Small omega will use for digital filter design. At omega equals to omega c. Okay, this omega c is the cutoff frequency. Clear? But we will see what will happen at omega equals to omega c. Then h of a j omega magnitude equals to 1 by square root of 1 plus, now this is 1 to power 2n, that is your 1 by root 2. Okay, you know that the frequency at which the magnitude is 1 by root 2 is known as a 3D frequency. Yes or not? Last class I explained. This is your 0.707. Okay, means the frequency at which magnitude equals to 1 by root 2 known as a 3D frequency. So we can say that omega c is a 3 dB cutoff frequency, 3 dB cutoff frequency for Butterworth filter, for Butterworth filter, irrespective of the order. Yes or not? it is irrespective of the order. Means whatever the order, it's not matter. Means what is the value of n, it's not matter. It's maybe 1, 2 or whatever, it's not matter. So now at omega equals to omega c, always you are getting this is 1 by root 2. So this omega c is known as 3 dB cutoff frequency for Butterworth filter. This is very, very important. Okay, 3 dB cutoff frequency for Butterworth filter. Now, what is the significance of this capital N? Already some people did. I think section C is completed now. Butterworth filter design in lab.
Yes, sir.
Okay, it's completed. See, now if you plot this, simple, I will show you here. First you finish this, I'm giving 30 seconds, then I will show what is the significance of this order. Okay. Completed, all of you? Yes or not?
Yes, sir.
Okay. Now see, you all people did the plot already. I will show you what is the significance of this capital N. Now, this is Butterworth filtered h of a j omega equals to 1 by r squared equals to 1 by 1 plus omega by omega c to power 2n. Okay. Now, if you plot this, if you plot, it's very, very important. Simple. I'll show you. Okay. Now, when you plot this, how you are getting the plot? You are getting in, I think in lab, you people already did. See, when you plot, I will show you how it is coming exactly. Yes or not? This type of plot you are getting. If you did the plot, okay, this is the magnitude 1, and this is your 3 dB cutoff frequency. So this is 1 by root 2, 0. Okay, for some value of n. Okay, if you did it's okay, otherwise you can try. If you plot this, this equation, this is equation A. If you plot for some value of n, any value of n you can do, it's not a problem. If you plot this, then you will get the plot like this. Okay, it's monotonically decreasing. Get it? Get it? Now, what you will do, simple, increase the value of n. Okay, increase the value of n. Again, you plot it. Let, for example, if you plot n equals to, let 3, then take n equals to 4, and again you plot it. Then what you will get? If you plot again, then you will get like this. See. Okay, you will get the plot like this. If you people did it, so otherwise you can try it. Now what you will do? Now let n equals 3, you will get this one. Then n equals 4, this one. Now again take n equals to 5. Okay, n equals 3, and see I'm using different color for different. N equals to 4. Now again let use n equals to some other value. Let n equals to 5 or 6 or anything, means more than that of 4. Then if you plot, you will get like this. Okay, get it? So what do people understand from here? Again, if you take more n value, high value, see, again I will use another, let n equals to, let more than value, 6 or 7 or 8, you can take any more value, then you will get like this. Okay. This is increasing value of n. Get it? Now see, student, it's very, very important concept. I shown here, if you try in the MATLAB, you try it, it's okay. Otherwise, you can try it. It's very simple plot. MATLAB code is very, very simple. But the MATLAB code, if you want, I can give the MATLAB code also. Simple. Take this omega value, anything, let it 0, 0.001, okay, to some pi or 2 pi also you can take. Okay, then take any value of omega c, not a matter. Omega c equals to let 1, 2, 3, anything you can take. Then what to do? Then simple, let it take n equals to n1 equals to 3, n2 equals to 4, n3 equals to 6, n4 equals to 7. Then simple, h1, you write this equation 1 by, okay, square root of 1 plus omega by omega c to power n1. Similarly, write other equation and simple plot it. Plot common. Plot, it's a simple omega comma h1. Okay, then hold on. Again plot omega comma h2. Okay, then again hold on like this, because we want multiple plot, and plot omega comma h3, then we will get this type of plot. Means, see what you observe from this. Can someone explain what you observe? If you see very carefully, yes. Now see, if you see very carefully what you people are understanding, see when the n value is increasing, then this practical filter approaching to ideal filter, yes or not? Agree? See the plots. Okay, if you do next plot, then again it will come like this. Yes or not? So what is happening when n is increasing, when the order of the filter is increasing, the practical filter is approaching the ideal filter. Or if you agree with me, yes or not? Now means what is happening? What is happening? Now if you see, let this is your stop band. Now slowly the stop band is shifting towards the water pass band. Yes or not? Means initially the stop band is here. Now slowly the stop band is shifting here. Omega s ds. Then again it is shifting here. Omega s double ds. Okay. Then it is omega s triple ds. Or yes or not? Now if you see here, the stop band is shifting towards the pass band. Now stop band is shifting towards the pass band means it is advantage or disadvantage? Yes. It's advantage or disadvantage? All of you. Yes or not? If people are getting or not? Huh? Section C and D. Just respond. When stop band is approaching the pass band, and shifting left hand side, it's advantage or disadvantage? Huh? It's advantage. It's a advantage. Why it's advantage? See,
Ideal filter.
yes, it's approaching ideal filter.
Ideal filter.
What happened? Then the noise which is after pass band, it will eliminate. Yes or not? Initially, you see the filter. Initially, your stop band is here and pass band frequency is here. Now, slowly, when the stop band is approaching here, means what will happen? Actually, ideal filter after omega p, for ideal filter, okay, simple. Omega greater than omega p means what? This h of j omega directly is 0. For ideal case, now means what is happening? Means when the frequency is more than that of passband frequency, automatically it is eliminating. Now when the stop band is approaching, then what will happen? Every case when n is more and more value and the stop band is approaching the pass band, means shifting left hand side. And if you see the plot, here, see here the plot, now see it is slowly approaching to, because why? If you plot next value means what will happen? See, it will come like this. Yes or not? It will come like this. Again, if you plot means slowly, it will approach to ideal filter. Then what will happen? When it will approach to ideal filter, then obviously the after omega p we don't want, because that is unwanted signal for us. Okay, so after omega p, it will block the signal. It will block the signal before. If you take small value of n, means what will happen? Since there is a transition band, band between omega p to omega s, you will get some value of signal, unwanted signal. Yes or not? Since it is done, because how is the plot? If you see, the plot is like this. The plot is like this. Since this period is the transition band, so what will happen? When you will use this filter after omega p also, because of this is not equal to 0. This is not equal to 0. Since it's not equal to 0, so what will happen? We are getting some unwanted signal. Yes, sir. But when you are increasing the value of n, when you are increasing the value of n, then what is happening? It's slowly approaching to ideal filter, means after omega p, the elimination become more and more. Yes or not? Because see, I will plot this. See, a high value of n, you will get like this. Okay, if you get like this, then means what will happen? See, so this portion will eliminate. See, these are very, very small value. The elimination means block rate is more or not? Yes or not, all of you? Section C and D, yes or not? People are understanding or not? Or you slept somewhere? Very
Understood, sir.
yes, sir. It's very simple. So means when you take a high value of capital N, obviously it is an advantage for the filter, because when n value is increasing, this stop band is approaching or shifting left hand side. Yes or not? The stop band shifting left hand side. Okay, shifting left hand side. Now, what is the meaning? When shifting left hand side means, I can say that say initially, if you see here, when n is small value, then the error is more. Error is more means what is the error? Error is 1 minus h of j omega magnitude. Means I will show you in another plot. See, okay, now I will show you two plots. This is one del P. So first plot is like this. For small value of n, simple. No. Okay, I'll give the first plot. Okay. Now, this is the first plot, and second plot for higher value of n, I will give another plot. Now this is your another plot. Okay, if this is n1 and this is plot for n2, obviously n2 is greater than n1. Okay, now see the error. I want to say the error part. If you see the error means your error is 1 minus h of a j omega magnitude whole magnitude. Now if you see here the error, see the difference. Means this is 1 and this is the plot and this is the error part. Okay, this is the error part of our first plot I am saying. Okay, now same case if you see the second plot for N2, then let the error is same 1 minus h of a j omega magnitude only. Now see the second plot. Now see this is the error. So the error is reducing or not? Yes or not? Because see these gaps are more. These gaps are more. Okay, compared to this gap. The error is reducing or not? Yes, all of you?
Yes, sir.
Yes or not?
Yes.
And if you go for another plot, see I will show you another plot. If you go for another plot later for more higher value of n, see this is the another plot for there. Let this is n3. Now see up to this point it's 0. Yes or not? Okay. So what is happening? So for n is increasing more and more, the error is decreasing more and more. Yes or not? Okay. Error means what? Simple you can say that the error between ideal and practical filter magnitude. Yes or not? For ideal case it is 1. For ideal case up to this is 0 to it is omega p or omega c we take. It is 1, yes or not? But practical case it is not 1. It's up to some value it is 1. After that it is decreasing. But when you increase the value of n, what is happening? Slowly it is approaching the ideal filter. Then what is happening? What's happening means this one become increasing up to some more extent. Yes or not? If you see in the first case, up to this value, the magnitude is 1. In case of second case, if you see up to this value, the magnitude is 1. But if you see in case of third case, see the filter magnitude is up to this, means it is slowly approaching. Yes or not? Let omega p1, omega p2, so omega p3. Okay. So in first case up to 0 to omega p1, the magnitude is 1. Second case 0 to omega p2, magnitude is 1. And third case 0 to omega p3 is magnitude 1. If you increase more and more value of n, again it will go and it will directly approach to omega p. Means the practical filter it will approach to ideal filter. And at the same time, see, this is happening in the passband case. At the same time, this is the stop band omega s1. Now it is shifted to here omega s2. Okay, it's omega s2. Now see it is shifted to here omega s3. Okay, so it is shifting towards the passband, means it is shifting left hand side. Getting all of you? So what is happening here? When you increase the value of capital N, the error is decreasing. Yes or not? So when you increase in the value of capital N, the error is decreasing. It's very, very important. Okay, increasing the order of the filter, increasing the order of the filter, error is decreasing. Error is decreasing. Agree all of you now? Yes or not? Section C and D.
Yes, sir.
Okay, so it's very clear. So when order is increasing, so what is happening? The error is decreasing. But what is the problem? Problem is we cannot design a high order filter, because by increasing the order of the filter, it will cost more and more. So what will happen? It will cost more and more and more and more, and also is required more manpower. Now just take one company. Say when you increasing order, one order also, it will cost little more. For example, for one order, let the increasing cost is something 1000 rupees. Let example. Then when how you are means manufacturing the chips. When you are manufacturing the fix, you are not manufacturing one and two. You are manufacturing balls, yes or not? For example, you are 1 lakh or 10 lakh, 10 to power 7, 10 to power 7 later chips you will design. Then just imagine when you increase the order value, okay, for increasing one order it is costing 1000 rupees, just for one example, 1000 rupees. Then to manufacture 10 to power 7 chips, 10 to power 7 multiply 1000, 10 to power 3. So that is 10 to power 10 rupees is coming extra. Yes or not? 10 to power 10 means how much it is? 1000 crore. Yes or not? Getting? Or if you take 100 also, if you take 100 also, how much is coming? 10 to power 9. So it is 100 crore. Okay, if you take a 10 also, then how much it is coming? It is coming 10 to power 8. That is 10 crore. Yes or not? Now just imagine if you design or manufacture higher order filters, then it will cost more and more, and also more manpower. Now what will happen if small defect come out? Then the company will shut. Yes or not? Getting? So because of this reason, it is difficult to design high order filter. All companies they are preferring to design low order filter only. Okay, and they are combining low order filter in different way to get the high order filter. Get it? Okay. Clear, all of you? Yes or not?
Yes, sir. Clear, sir.
It's a very simple way we can say. So what you understand, when order is increasing, the error is decreasing. Simple, when order is increasing, the stop pen is shifting left hand side. That is advantage. Okay, we can take liberty on the stop pen, no problem. Okay, and also when order is increasing, this idle practical filter is approaching to idle filter. That is advantage for us. Okay, and my suggestion is better you try this, all of you. Already you did in the MATLAB. Okay, now who is the faculty is taking MATLAB for you people? Section C?
Myself.
You, sir, Kalyan Matra. Okay, sir.
Yes.
So these people will do this program, sir, just to verify it. Okay.
Okay.
And I will ask you people also to send the code and show me the output. Okay. So this is very simple program. And same people D, section D people you take as an assignment. This is you just prove that by using MATLAB, when order is increasing, this plot is shifting left hand side. Okay, the plot is shifting left hand side. Clear? So this is very important thing for Butterworth filter. Okay, for Butterworth filter. Now see. This is what you understand. This is simple. Again, I am writing h of j omega magnitude is 1 by square root of 1 plus omega by omega c to power 2n. Okay. Now you understand that that omega c is your 3 dB cutoff frequency. And also, okay, this when order is increasing, the error is decreasing. Error is 1 minus h of a j omega magnitude. Okay, it is decreasing. It is decreasing. But again, I explain you people why it is difficult to manufacture a high order filter. So all companies are always preferring to design minimum order. Okay, design minimum order, because the high order it's required more manpower and it will cost more also. Okay, now see, if you see the plot, it is monotonically decreasing. Yes or not? If you already shown, if you see these plots, see these plots is monotonically decreasing. Okay, now one important property again I will show you. The important property is we can write this h of j omega like this. H of j omega magnitude equals to 1 plus omega by omega c to power 2n to whole power minus half. So that is equals to 1 minus 1 by 2 omega by omega c to power 2n plus we'll get some higher order, yes or not? Higher order of omega by omega c to power 2n. Yes or not? It's very easy. This formula also people know 1 plus x to power minus n equals to 1 minus x, yes or not, plus n n minus 1 by 2 factorial x square plus like this you will go. Okay, or we can say it is a, or I will give another formula, same, it's very simple formula. If you confuse about minus pattern, see 1 plus x to power n equals to 1 plus nx plus n into n minus 1 by 2 factorial x square plus n into n minus 1 n minus 2 by 3 factorial x cube, and it will go like this. Now see, here simple replace n by minus 2, minus 1 by 2. Okay, simple replace n by minus 1 by 2. So first we get 1 minus nx, because n is minus half of 1 minus half x. 1 minus half x is omega by omega c to power 2n. Plus what next you will get? Next is minus half minus 1 by 2 factorial x square. Okay, the coefficient just you left. I'm not thinking much. X square. X square means omega by omega c power 4n. Then some part omega by omega c to power 6n. Yes or not? You will get like this. Now, this is h of 8 over j omega. It is 1 minus 1 by 2 this portion plus higher order of omega by omega c. Now, if you differentiate by with respect to omega, okay, and if you put omega equals to 0, then what will get? We will get here 0. Yes or not? Because if you differentiate means what? The first part becomes 0. There is no doubt. First part becomes 0 minus 1 by 2. Then it is 2n omega by omega c to power 2n minus 1 multiply 1 by omega c. Plus same thing will happen. So everywhere we get this omega portion. So when omega equals 0, finally 0 minus this is also 0. Again you will get all zeros. Okay. So finally we get 0. Clear? So similarly up to what value you will go? Means my point is here. If I will do the differentiation like this, dh of a j omega by d omega, let I time I am going for the differentiation. I time. Okay. Okay, then how many differences will get a constant value? This is 0 for I equals to 2n minus 1. Okay, for I equals to 2n minus 1. Yes or not? It will go, or we can say like this, for I equals to 1 to 2n minus 1. After that what will happen? You will get some constant value. Yes or not? All of you? See, I will show you here one example. Let y equals to x square. Then dy by dx is 2x. Then d square y by dx square equals to 2. Yes or not? See, simple. It's here n equals to 2. Okay. So now dy by dx for x equals 0 equals to 0. But d square y by dx square x equals 0 equals to some constant. Okay. So up to how many terms you are getting 0? That is the question mark. See, this is dy means 1 and this is 2. Okay. Means now if you take here I, if you take here I, then what will happen? When I equals to 1, so we can say that di y by dxi for x equals 0 equals 0. 1 means what? Yes, sir. 1 means it is 2 minus 1. Yes or not? That's why if you see here, see back side, see here, it's order is 2n. This order is 2n. So up to 2n minus 1. If you compare this, here order is 2. up to 2 minus 1, we will get 0. See, I kept same thing. Up to 2n minus 1, simple here, 2n equals to up to 2n minus 1, it is 0. But when I equals to 2n, because see, when I equals to exactly 2, you are getting some constant. The same way, when I equals to 2n, then di h of a j omega magnitude by d omega equals to 0, we will get some constant. Okay, we'll get some constant. Getting? Now, here what is the property? The property is when the function gives 0 for single differentiation. Okay, when the function gives 0 for single differentiation, you can say that it is a flatter point. Flatter point means, see, I will show you here. Flatter point means this is the flat point. Okay, or you can say this is the flat point. The flatter point. Okay, flatter point means if the function here h of j omega is the function, correct? If the function gives 0 for single differentiation, we can say that it has only one flatter point. One flatter point means it may be maxima or it is a minimum. Okay, single flatter point or single flatter point. But here in this case, in case of Butterworth filter, what you understand? See, I will show you here. See, this is the flat point. Or if one I will write also, when function gives 0 for single differentiation, then it is called flatter at this point. Flatter at this point or at that point. Okay, at that point. Okay, means means any function. If any function gives 0 for single differentiation, let this is the function. Yes or not? F of x is the f of x equals to x squared. So this is single differentiation gives 0 value. So what you can say that it is either maxima or minimum. Okay, it is either maxima or it is a minimum. But if you see in case of Butterworth filter, what is happening? The function is giving so many 0 values. Is not d h of j omega by d omega. This is I. Now this is equals to 0. I equals to 1 to 2n minus 1. Yes or not? So for single 0 value, it is called flatter. Okay, it's called flatter, means only single flatter point, means single either maximum or minimum value. But here we are getting how many? 2n minus 1 number of time 0. Yes or not? Getting the Butterworth filter gives 0 value for so how many? 2n minus 1 number of time of differentiation. That's why we can say that it is a Butterworth filter has a maximally flat. You can say Butterworth filter has a maximally flat, means more than one flat value. Maximally flat at omega equals to 0. Okay, for single value of differentiation 0 means it's single flat value, but here it's more than differentiation is 0. It's up to 2n minus 1 time the differentiation is giving 0 for omega equals to 0. Hence, it is a maximally flat at omega equals to 0. Clear all of you? Yes or not? section C and D.
Yes, sir.
Okay, so this is the way. So this is very important property. So Butterworth filter having maximally flat at omega equals to 0. Okay, so this is a Butterworth filter has Butterworth filter has a maximally flat, or it's known as also you can say that you can say has a maximally flat, has a maximal means so many, more than one, maximally flat at omega equals to 0. This is one important property. Important property of Butterworth filter. Okay, clear? Now we will go for what is the asymptotic behavior. Okay, now we will go for asymptotic behavior, means how it is changing, the behavior or characteristic, how it is changing. Okay, now see h of a j omega magnitude equals to 1 by square root of 1 plus omega by omega c to power 2n. Now when omega is infinity, when omega tends to infinity, very high value, okay, we can write h of a j omega magnitude equals to 1 by, now see, omega is very high value means what? 1 plus high value equals to high value, so we can write like this: h of a j omega is approximately equals to this square root of omega by omega c to power 2n. Is not, means for example 1 plus 10 to the power 6, it is nearly equals to 10 to the power 6 only, same meaning. So then it is equals to omega is equals to omega by omega c to power minus n. Okay, omega by omega c to power minus n. Now if you take log both sides, if you take simple 20 log h of j omega magnitude equals to minus 20 on 20n log 10 omega by omega c. Then what is the meaning? Meaning is when omega is increased by a factor of 10, okay, omega is increased by a factor of 10, then the characteristics goes down by minus 20n. Yes or not? Because minus 20n. For example, see, it's very simple. If omega equals to 10 omega c, then what will happen? This is 10 equals to minus 20n. Now if omega equals to more multiple of 10, 100 omega c, then what will happen? It's 100, then it is a minus 40n. If omega equals to again multiple of 10, it is 1000 omega c, then what will happen? It is minus 60n. Yes or not? See, so what is happening? This negative value means the plot will shift down. The plot will shift, or the complete the characteristics will go down. Yes or not? So thing is, if omega increases by 10 or multiple of 10, when omega increases by 10, then the plot or the characteristics will goes down by 20n. Goes down by 20n. Yes, 20n. And if omega is a multiple of 10, multiple of 10 means it is also multiple of minus 20. Multiple of minus 20 means minus 20n, minus 40n, minus 60n, and minus 80n, like this. Okay, so we can say that what is the asymptotic slope from here? The asymptotic slope is it is a minus 20n dB per decade. Okay, means see, decade means it's 10, yes or not? Now, when it's very simple meaning, means if omega increases by 10, then the characteristics goes down because of this negative sign, goes down by 20n, Hence the asymptotic plot is minus 20n dB per decade. Okay, it's increased by a factor of 10, it will decrease by 20n. Okay, so this is another, it's very important property of Butterworth filter. Okay, very important property. Clear all of you? Yes or not? Okay. Now next class we will discuss some more points and we'll go for the derivation part. So this is very important. See what we discuss today. All points are very important. We start. This is the equation of Butterworth filter. Okay, and when you increase the value of n, it's very important. The practical filter approaches to ideal filter, or you can say that the stop band frequency is shifting towards pass band, or you can say that the stop band is shifting left hand side. Okay, for a higher value of n, this I given as assignment you have to do. Okay, but important thing is you cannot go for higher value design a higher value of n because it requires more manpower and more cost. Okay. And also one important thing, what when order is increasing, the error is decreasing. Same thing. That is a practically is approach to ideal. When order is increasing. Okay. After that, we just shown how this things happening as well from the figure. Then this is we got that when you are doing differentiation of this magnitude of this filter response. What you are observing up to 2n minus 1 point, you are getting the differentiation equals 0 or omega equals to 0. For omega equals to 0, okay. For single differentiation equals to 0 means you can say that it's a single flat point. It's either maxima or minima. But here not single. You are getting what? So many means 2n minus 1 time of we are getting a 0 value. Okay. So hence it is a maximally flat. It is a maximally flat. That is after that we discuss just 1 minute. After that this is I saw the flat point maxima or minima single flat point for single deviation equals 0, but here getting differentiation equals 0 for multiple value of omega. Hence it is a maximally flat. This is very important. It's a maximally flat. And finally, we just 1 minute. Okay, and finally, we discuss this asymptotic behavior and what you observe that when this omega, we observe that when this omega is increasing by a factor of 10, then the complete characteristics is decreasing by 20n. Okay, this we got. Okay,